the result is important, that these equations are equations that can be used for elastic collisions. So these equations that we just derived let us very simply and straightforwardly solve a problem like this. So we say we've got a ball with mass 0.25 kilograms, it's moving at 5 meters per second. Second ball of mass 0.8 kilograms is initially at rest. They collide elastically and head-on. We're going to find the final velocity of each ball. Well, we can just use those equations that we derived. V1 final is the ball that's initially moving, is V naught, which is 5, times M1 0.25 minus M2 0.8 over M1 plus M2. So we can stick that in. We can punch that in. Take 5 times 0.25 minus 0.8 over 0.25 plus 0.8. Oops, 0.8. And get minus 2.619 meters per second. And the negative means that it's going in the opposite direction of where it started, which is actually always the case. If you have a smaller ball and it runs into a smaller object and it runs into a bigger object, most of the time it's going to bounce back. So that's a perfectly reasonable result. V2 final, just plugging in from our equation, is 2 times M1 is 0.25 times V naught, 5 over M1 plus M2. And again, we can punch that in. 2 times 0.25 is 0.5 times 5 is 2.5 divided by 0.25 plus 0.8. We get 2.38-ish meters per second. So we can solve our elastic equation simply and straightforwardly once we know the equation that results from all of that nasty algebra. Collisions in 2 dimensions follow the same principle of conservation of momentum, but we just have 2 parts. We have momentum conservation in the x direction, and we have momentum conservation in the y direction. And so we write out conservation of momentum in both directions. For example, let's say we have a truck with mass 3,200 kilograms. It's driving south at 11 meters per second, while a car with mass 2,100 kilograms is driving east at 15 meters per second. They collide, move together. I want to know what is their velocity after the collision. Well, in the x direction, our initial momentum, the truck initially has 0 momentum. So in the x direction, we just have the momentum of the car, which is traveling at 2,100 kilograms east. Okay. And then afterward, we have the 2 of them moving together. So that's our conservation of momentum equation in the x direction. In the y direction, initially we only have the truck. The car is moving due east, so it has no y momentum. Moving south at 11, so we do a minus 11, and that's going to be equal to the combined mass times their final velocity in the y direction. So we can get their final velocity in the x direction. Take 2,100 times 15 divided by 2,100 plus 3,200. Get our v final x is 5.94-ish. I'm going to store that as x. And then in the y direction, 3,200, times minus 11 divided by 2,100 plus 3,200. We get our v final y is 6.64 minus about, store that as y. So our v final, we just do the magnitude, square root of the x component squared plus the y component squared. So our v final is 8.9125 meters per second. And the arctangent of y over x gives us minus 48. This was positive x component, means we're east. Negative y component means we're south, so that's east. 548.175 degrees south. So that is how we would find our final velocity. And actually, they can, when there are collisions, they apply conservation of momentum as well as kinematics, based on where the cars are from where they hit each other, to determine the speeds at which the vehicles were going when they collided. Another example of a 2D collision is something like this. This is going to be a little more complicated. So you got a pool cue ball with mass 160 grams, and it's going to strike the 8 ball, which has a mass of 155 grams. The cue is moving due west with speed 8.6. After the collision, the cue moves with speed 3.1 meters per second at west by 12 degrees south. We want to find the final velocity of the 8 ball. And again, we're going to apply conservation of momentum in the x direction, conservation of momentum in the y direction. So in the x direction, the cue ball was moving due west, 160 grams. So due west, well, you got 160. It's moving due west at 8.6. That's minus 8.6. The 8 ball wasn't moving, so that's our initial momentum in the x direction. After the collision, the cue, mass 160, moves with a speed of 3.1 meters per second at west by 12 degrees south. So the x component of that is minus 3.1 cosine 12. And then we have the 8 ball going off with some v final x. In the y direction, we have zero initial momentum because the cue ball is moving west, so it doesn't have any y velocity, and the 8 ball is at rest. And so then that is the y component of the cue ball's momentum plus the y component of the 8 ball's momentum. So we can punch that in. I don't have quite a space here. So our v final x is going to be 160 times minus 8.6 plus 160 times 3.1 cosine 12. If we move that over, divided by 155. Oops, I did times 155. Divided by 155 gives us minus 5.747. Total store is x. And then in the y direction, we just have 160 times 3.1 sine 12. It's positive because we're moving it over to the left side of the equation. Divided by 155 gives us 0.665. Store as y. So the velocity final of the 8 ball is 5.7857, etc. meters per second at our tangent of y over x. Negative x component, positive y components, that's west by 6.603 degrees north. Alright. And in this case, the 8 ball was initially at rest. The pool cue is moving due west. In general, both balls could have components in the x and y directions initially, in which case you just plug those into the equation. If the 8 ball had been moving, say, east, then this would just have a plus 155 times v naught of the 8 thrown in there. And if it was moving at an angle, you'd throw in those velocities with the trig functions as well. And so 2D follows the same principles as 1D, it's just that then you have two equations to solve for.